Hi everyone, this is Kiranmay from H&S department. Today we are going to discuss about particle in one-dimensional box, the behavior of a particle in a infinite potential well. So to discuss about the behavior of particle in one-dimensional box, let us take a box of width A which is extending only along the x-axis. The box is extending only along the x-axis. So whose limits are from origin to a distance of A on the x-axis, from origin to a distance of A from the x-axis. So this is the box what we have taken, whose axis is extending only along x-axis, and it is having a limits from x equal to 0 to x equal to A. Okay, and this is an infinite potential well. Here in this, we are going to take one particle whose mass is m and it is randomly moving inside this walls. Okay, and since the walls, since the potential energy of this particle between these walls is constant, so there is no force acting on this particle. So since there is no force acting on the particle, the potential inside the well will be equal to 0, and potential acting on the particle will be equal to infinity outside the well. So for that, if you write the same thing in conditions, so this is the condition where V of x potential will be infinity outside the well. Outside the well means before first wall and after the second wall. Here the particle is outside the well, the potential will be infinite. When the particle is inside the well, the potential will be equal to 0. These are the two conditions what we are supposed to apply. Now just take the Schrodinger wave equation for a particle which is given by dou square psi by dou x square plus 8 pi square by h square m into E minus V of psi equal to 0. So now if you can convert this Schrodinger wave equation, when you apply the same thing for the particle which is inside the potential well. Inside the potential well, if the particle is inside the potential well, potential will be equal to 0. So apply the same condition in the Schrodinger wave equation. So if you put potential energy as 0, the expression will change like dou square psi by dou x square plus 8 pi square by h square m E minus V will be there, that will be 0. So E into psi equal to 0. Now take this constant associated with wave function, that is 8 pi square by h square me as a constant k square. Okay, so let 8 pi square by h square me will be equal to k square. Now you can write the expression as dou square psi by dou x square plus k square psi equal to 0. This is an expression which seems to be a second order differential equation. D square psi plus k square psi equal to 0, where d square is equal to dou square by dou x square. Okay, so now psi, if you take psi as common, d square plus k square of psi equal to 0. So this is a second order differential equation whose solution will be in the form of psi of x is equal to a sin kx plus b cos kx, where these two, a and b, are called as constants which you can obtain from applying boundary conditions. What are the boundary conditions here? X equal to 0 is the first boundary, x equal to a is the second boundary, where when a particle comes at the walls, there is no moment for the particle. Hence, at the walls, x equal to 0 and x equal to a, the wave function will become 0. This is the boundary condition which you have to apply for this solution, so that you can obtain the values for constants a and b. So let us apply first condition to the solution. What is the first condition? Wave function will be 0 at the first boundary, x equal to 0. So solution is psi of x is equal to a sin kx plus b cos kx. Now apply the equation to this one. a boundary condition to this one, psi will be 0 at x equal to 0. So 0 is equal to a sine 0 plus b cos 0. What is the value of sine 0? 0. Cos 0 is 1. So the expression will change like 0 is equal to 0 plus b. So b equal to 0. Now if you substitute the same in this expression, b equal to 0, the second term will become 0. So left off with psi of x is equal to a sine kx. Now apply second boundary condition to the above expression. So what happens? Second boundary condition is psi equal to 0 at x equal to a. Now apply the same thing to this one. 0 is equal to a sine k. A sine k. This will be looking like a into b equal to 0. So from this, either a should be equal to 0 or b should be equal to 0, which means that capital A should be equal to 0 or sine ka should be equal to 0. So what happens if a equal to 0? If you make a equal to 0, both the constants will become 0 and there is no solution for the wave function. To avoid it, a should not be equal to 0. So if a is not equal to 0, definitely sine ka should be equal to 0. If sine function is equal to 0, when sine function will be 0? At the values of sine 0, 0, sine pi 0, sine 2 pi 0. So all the values of n running from 0 to infinity, if it is multiplied by pi, sine value will be equal to 0. So sine ka is equal to sine n pi. So on the both sides sine function is there, so ka is equal to n pi. If you rearrange the terms, ka is equal to n pi by a. Now therefore you can write the wave function as psi of x is equal to a sine n pi by a of x. Till now we didn't find the value of a, but we got a value for constant k. Okay. Now, as we consider k square is equal to 8 pi square h square m into e, and here we got k is equal to n pi by a, then k square is equal to n pi by a whole square. Since both the values are same, you can equate them together. If you equate them together, you'll get by the rearrangement on both sides, you can cancel pi square. And by rearrangement, you'll get en is equal to n square h square by 8m a square. Which is from this it is clear that energy is having discrete set of values. If you change the n value, energy value also changes. Hence we can say that energy is quantized. Okay, for n equal to 1, if you place n equal to 1 in this expression, you will get h square by 8 ma square. If you put 2 square into h square by 8 ma square, you can write it as 2 square into first energy E1. Similarly, for E3, you can write it as 3 square into E1. For E4, 4 square into E1. In the same way, in general, you can write it as En is equal to n square into E1. Hence, we can say that energy is quantized. Okay. But our task is to find out about the constant A. So to find that constant A, just apply normalization condition to the solution. What we get? What is the solution we got? Sine of x is equal to a sine n pi by a of x. Yes. For this, just apply normalization condition. The normalization condition is volume integral modulus psi square dx dy dz equal to 1. But here we are just taking a one-dimensional box. So this volume integral can be changed to line integral modulus psi square dx is equal to 1, which is extending from first wall x equal to 0 to second wall x equal to a. So what is psi? Psi is nothing but a sine n pi by a. Psi square is a sine n pi by a of x whole square. So just applying the square, a square sine square n pi by x dA equal to 1. So since a is a constant, you can get it out of the integration. A square is integral sine square n pi by a x dx equal to 1. We know that from the trigonometrical formulas, cos 2 theta is equal to 1 minus 2 sine square theta. Just rearrange the terms, you'll get 2 sine square theta is equal to 1 minus cos 2 theta. Sine square theta is equal to 1 by 2 into 1 minus cos 2 theta. Here in this formula also you can observe that sine square, the theta value is like n pi x by a. So apply this formula 1 by 2, 1 minus cos 2 theta here. So it will be like 1 by 2 into 1 minus cos 2 into n pi x by a. So integrated, since 1 by 2 is also a constant, get it out of the integration. A square by 2 integral 1 minus cos 2 n pi x by a dx equal to 1. Now integrate it individually. Integration of 1 is x. Integration of cos theta, integration of cos 2 theta d theta is equal to sine 2 theta by 2. Okay. Here the theta value is n pi by a x, n pi by a into x. Na? So the value is like integral cos 2 n pi x by a dx. For this, the integration will be like sine 2 n pi x by a by 2 n pi by a. So this in the denominator will get reversed. This will be like a by 2 n pi sine 2 n pi by a of x equal to 1, where the limits are running from 0 to a. Now applying the limits in place of ax, upper limit minus lower limit, that is a minus 0. Here in this term also applying the limits in place of x, sine 2n pi by a into a minus sine 2n pi by a into 0. So this is like a. This one a cancel, sine 2n pi will be 0. Here also sine 0 is 0. So the total term will become 0. So a minus 0 is equal to 1. A square is equal to 2 by a, and a is equal to root 2 by a. So from this you can write the wave function as sin of x as root 2 by a sin n pi by a of x. This is in case of one dimension, where n is called as eigenfunction and en is called as eigenvalue. If you want to write the same thing in 3 dimensions, in 3 dimension, how do you write it? This one is along the x-axis. In y-axis, let it be b. In z-axis, the distance between the walls will be c. Then you can write it as root of 2 by a into root 2 by b into root 2 by c. This is along x-axis, y-axis, and z-axis, x, y, and z. So sine n1 pi by a x into sine n2 pi by b of y, sine n3 pi by c of z. So, and eigenvalue, you can write it as n square by 8mv square, where n square value is summation of values along x-axis, y-axis, and z-axis, n1 square plus n2 square plus n3 square. These are the eigenfunction and eigenvalues of the particle which is in 3-dimensional box, and this is eigenfunction in 1-dimensional box. Okay, so let us see one problem regarding this eigenvalue of a particle. Here in this, they had given a 1-dimensional box of width 0.1 nm, and they were asking you to find out the lowest energy. The lowest energy, the lowest value that we can give for n is 1. So we can write it as n equal to 1, and width of the box as 0.1 nm. So substituting those values here, in this formula, this is H Planck's constant, whose value is constant, 6.6 in 10 power minus 34. This is in the question they had mentioned that particle is electron. So mass of electron is 9.1 into 10 power minus 31. And they had given the width as 0.1 nm. So you can convert nanometers into meters as 1 nanometer is equal to 10 power minus 9 meters. Just using this one, you can change the values from 0.1 nm to 0.1 into 10 power minus 9 meters. Just substituting the values and rearranging them, you will get a value in joules. Now to convert joules into electron volts, 1 electron volt is equal to 1.6 into 10 power minus 19 joules. So if you want to convert joules into electron volts, just divide it with 1.6 into 10 power minus 19. You'll get a value in electron volts. Let us see one more problem in the same way. Here in this, instead of giving one-dimensional box, they were asking a question regarding the energy of an electron immediately after the lowest level, confined in a cubical box. Cubical box means it's a three-dimensional box. So for 3 dimensions, they were asking you to find out the energy of the level which is just after the lowest level. Just after the lowest level means for lowest level, N1 is 1, N1, N2 is 1, and N3 is 1 for lowest level. Just after the lowest level means just increase the value of N3 by 1. Then N1 is equal to 1, N2 is equal to 1, and N3 is equal to 2. This is the level which is just after the lowest level. So substituting them together in the formulas, like n square is equal to n1 square plus n2 square plus n3 square. So substituting them together and doing the mathematical calculations, you'll result with a value in joules. To convert that into electron volts, just divide it with charge of electron, that is 1.6 into 10 power minus 19 electron volts. Okay, so this is in case of a three-dimensional box. This is also some problem regarding a one-dimensional box. They were just asking you to find out the energies of ground state and first two excited state. Ground state, there's no doubt the n value will be 1. First two excited statements, first excited statements n equal to 2, then second excited statements n equal to 3. Just taking different n values, you can find out these values like as they had mentioned the particle is electron, you can take the common values for Planck's constant mass of electron and substituting different n values for the different states and doing mathematical calculations, you'll result with different energies of E1, E2, and E3. This is one more problem where you are going to use the general formula for energy. Where they had given the minimum energy of the particle in a one-dimensional box. That is, they had given minimum energy means n equal to 1. So if they had given the energy E1 in terms of joules, and they were asking you to find out the energy of next 3 energy levels in electron volts. So to avoid the complication, I'm just converting the minimum energy into electron volts by dividing it with charge of electron, that is 1.6 into 10 power minus 19 with the given value. So the value will be changed in like 20 electron volts. This was the minimum energy of the electron or a particle which is confined in one-dimensional box. As we had derived one general expression for the energy, that is En is equal to n square E1. E1 value they had given. They were asking you to find out next 3 energy levels. That means n equal to 2, 3, and 4. Just substituting them in this general formula, you'll get energies of next 3 energy levels. This is one more from formula where they had asked you to see there are 2 energy levels, ground state and next first excited state and second excited state. So they were asking you to find out to pump an electron from E1 to E3, how much energy is required to pump or to lift an electron from E1 to E3. How much energy is required, they were asking in the question. For that, what we are supposed to do, we are finding the energy of third level, that is second excited state, and the energy of ground state. Just subtracting them together from one another, it will give you how much energy is required to lift the electron from ground state to second excited state. Okay, for that we just taken the help of energy. En is equal to n square h square by 8 mu square. Using this formula, we had finded the minimum energy of the particle or the electron which is in the ground state, and we had converted that into electron volts by just dividing with charge of electron. After that, find out the energy of second excited state, that is E3 value, using general formula En is equal to n square E1. As we had finded E1, now we are finding E3 value using 3 square E1. So using that, you will get the E3 value. Just subtracting E3 minus E1 will give you energy required to pump the electron from first energy state, that is ground state, to second excited state. Okay. Thank you.